Hi, my name is Austin Mason. I am going to be talking to you about ARQ-531, which is a relatively new drug that came out a couple years ago. Um, it's a cancer treatment drug. Now, there are other drugs in the field, and I'll be getting onto that later, comparing and contrasting them a little bit, why it's such a great revelation in terms of cancer treatment. Um, I unfortunately have not done any research with anybody, so all this information is coming from me just reviewing research articles online. I have links to those in the PowerPoint if you'd like to go read them yourself. They go a lot more in detail than what I'll probably go into here. But the goals for my presentation are to introduce cancer in the first place. Most of us, well, all of us, have some type of background in chemistry at this point, so we'll probably all know a lot about cancer, whether we wanted to or not, but cancer is really interesting, so it's fun to talk about, and it's the main reason why I picked this as a topic, because it's just a cool subject to talk about. The type of enzyme, or the specific enzyme that the drugs inhibits is called BTK, and I'll introduce it more here in a minute after I get done talking about cancer. I'll talk about a little bit about the pathway. It's a little important. I'll try and do the Cliff Notes version of it basically. And like I said, I'll compare and contrast some of the other medicines. I have a few of the structures. And then finally, we'll look at the drug itself, and I have a few test data put towards the end to look at. I also have some few structures of that, like anatomical models type thing. Alright, so what is cancer? Why do I have this slide here? What's so important about it? What's going on? So to start off, cancer is a mutation of cells. It's actually a group of mutations. Your body and their cells naturally have a bunch of enzymes and pathways in place, like a ton of them, that stop cells from doing things that they're not supposed to and just in general regulate how cells are supposed to function. And when enough of those mutations culminate together, you end up with what's called a cancer cell. As seen here on the right, I have, if I can draw right here, this is a liver with cancer. I'm not exactly sure what kind. I just pulled this image off of, I believe, Google Images. Um, but what can happen with cancer is cells can end up where they're not supposed to be, or even the cells that are supposed to be there will just grow out of control, and you end up with all these little tumors, like right here, here, here. They're all over the place. Now, a common misconception is like over here on the left, a tar-filled lung versus a healthy lung. This is lung cancer. And me as a kid and a lot of other people had this misconception that this is what cancer looked like right here. Ooh, eh. um, there. And the reason is because there were a lot of non-smoking commercials that basically said exactly that. This is what cancer looks like. This is what it does to your lung. And while this is definitely a lung cancer patient, the tar is from the cigarettes that you smoke in. It's not actually the cancer. The cancer is the mutated cells, and the tar just facilitates that mutation. So it's a big misconception of what cancer actually is, and I wanted to touch on that. You don't see commercials like that actually. I haven't seen them in years now, but it's what I used to think cancer was until I got into college and learned a little bit more about it. All right, third time's a charm. I want to talk about three types of cancer, overall types. You have benign, malignant, metastasizing. So on the left, we have normal cells. Normal cells can undergo mutations which stop them from aging or blowing themselves up with apoptosis. They can become right here, which is called benign cells. Now, benign cells can sometimes grow in size, especially if they're located around a growth plate. They can just massively grow and grow and grow and grow and get really big. But what's more common is for them to start multiplying a little bit and become what's called a malignant cell. And malignant cells can grow and grow and grow and become a massive tumor, and it can get really dangerous. But as they grow, they can eventually become unstable and burst almost, and this is called metastasizing, and it's where they spread. to other neighboring cells, and it's the most dangerous form of cancer. I actually had a version of benign cancer, and it was in my leg. It was called osteochondroma. They cut it out, and after doing some tests, they're like, "Oh, it's benign. You're okay," because it wasn't spreading. So after it's gone, no more problem. And we're not going to go too in detail here. There's a lot of technical jargon on this slide, but what I want you to focus on is just the spreading of cancer. Here's some cancer cells. You can tell them by the elongated shape. They're squeezing through other cells basically to move about your body, which becomes a real problem when they get into one of the superhighways in your body. Say like your blood cells, for example. Blood cells, blood veins, arteries, that type of thing. Now, another common way is your lymph nodes. Your lymph nodes are another superhighway for white blood cells, and anything really dangerous can get in there because blood cells pull them back into your lymph nodes to help fight them. And so when cancer gets into one of these superhighways, it can spread into a lot of places, and it's where things can get really bad. You can have things like what I showed on the first slide. You can have someone's lung growing inside their liver, for example. Someone's heart growing inside their liver, stuff like that. Alright, so the specific type of cancer we're going to be talking about today is chronic lymphocytic leukemia. Now, like I said earlier, cancer can enter your lymph nodes, and your lymph nodes are super high throughout your body. They go to your blood cells, they go to your bones, they go to your spleen, they go all over your body. So if cancer gets into your lymph nodes, it can be really bad. Well, this is slightly different than that. This is lymphocytic leukemia. This is an overproduction of white blood cells. As the stages of it slowly progress, there are 6 stages. You have more and more and more white blood cells in your body, and it'll slowly begin to take over your body, and you'll have fewer and fewer platelets and red blood cells until you eventually die because you don't have the ability to clot blood with the platelets, and you don't have the ability to really carry oxygen with your red blood cells. You'll just slowly be killed off by that. It can also cause clots and all kinds of other problems in your body. Now, when it comes to treating CLL, there's a lot of different options. But the thing is, what options they use is generally determined on how severe it is. In general, they would try to stay as low as possible as they can on what treatment they use, and they only use severe treatments for people who are really in need of those severe treatments. They basically don't have other options at that point. So the first couple things they do is if you're a low level, they're not really sure if you have it or not, so they'll just put you into observation and they'll wait and see what happens. Does he actually have CLL? After that, they might try radiation or chemotherapy, and then after that, they'll attempt targeted drug therapy. Now, the reason targeted drug therapy is currently so low on this list is because the drugs that we currently have are not super selective, which can cause a lot of problems in your body. So it's very dangerous, and you already probably know how dangerous, or at least have seen some effects of both chemo and radiation. So looking at how low this is below those, that should give you a general idea of why this is really good that we have new medicine coming out in this field. After that, immunotherapy is pretty low on the list. It's not because of how dangerous it is, which it is really dangerous. It's just not as reliable, it seems. That from what I've read, it seems like it's kind of a side option. But immunotherapy, what that is, it's basically increasing your body's ability to help defend itself, which you might think that's great, but then you also run the risk of your body attacking things it shouldn't and giving yourself basically a artificial autoimmune disease, kind of. Your body killing stuff it shouldn't be killing. And so there are risks with all of these, including observation. Like, you might think, how's there a risk with observation? But if somebody actually does have CLL and you're just observing it, That's time you could be spent doing these, but again, you don't want to jump directly into these because they're dangerous. And having new drugs that are less dangerous is amazing, and that's the whole point of this. Alright, so let's really start getting into it. What is BTK? What effect does it have on CLL? And why is it so important? Alright, BTK, as I said before, is an enzyme. It is specifically a kinase. Now, a kinase phosphorylates something. What that means is it takes a proton from ATP and puts it onto something else. It's generally what it does. It's extremely important. It's a very simple job, but you need it to live. A lot of toxins like cyanide are working by stopping the phosphorylation of something. It is also very important because it acts in oncogenic signaling. It's part of what's called the BCR tract. That's a lot of jargon, but basically what it means is that when BTK is phosphorylating stuff, everything's happy, the cells are fine. If something inhibits BTK, it causes a chain reaction that leads to the cell destroying themselves because the cell recognizes that something is wrong with it at this point, and it's usually thinking that it's cancer. And so a common thing in cancer, specifically CLL, is an upregulation of BTK. You'll have more of it and it'll be working harder. Because if you have more of it and it's working harder, it's harder to inhibit and you won't blow yourself up as much. It's just general preservation. CLL in general will downregulate processes or chromosomes that specifically reduce its effectiveness to grow and spread, and upregulate stuff like BTK, which helps it survive. Alright, so this is a ribbon model of BTK. It has beta-pleated sheets and alpha helixes. Now, you might think those are two different subunits, which when I first started looking at this, I was like, what are the subunits? How many are there? I wanted to know details like that, but the thing is, it's all one subunit, which is kind of crazy that something that's only one subunit can control whether or not you live or die. That just seems interesting to me. I've had a little more I want to talk about on this slide, but I'm getting a little pressed for time, so for now, here's just a general picture of BTK in a ribbon form. Enjoy that. And here's the BCR pathway. Like I said before, when you have a phosphorus with BTK, it's doing its job, it's phosphorylating C2, and it leads to the inhibition of apoptosis. The cell does not blow up, basically. When something acts on BTK, it then goes to here, and it does lead to blowing up. That's very, very, very abbreviated. It's a very crude way of saying that, but these pathways can get extremely in detail. And if you've taken biochem, you should probably recognize this right here. That should seem really familiar. I'm just going to leave that there. Alright, let's talk about the current options for treating, not curing, but treating CLL. These options have been very effective. The most effective has been this one right here, ibrutinib. It's hard to say, but it is currently the widest used of these three. And something I want you to take note in is that all of these are covalent inhibitors. That's very important when we get on to talking about the difference between this and ARQ, because spoiler alert, ARQ is a non-covalent inhibitor. And if you look right here, they all have this similarity to them. A bunch of carbons and hydrogens together, usually double bonded, able to bind to stuff easily. Specifically, it binds to the cysteine 481 right here. This is your binding site. This is your ATP binding pocket. This whole pocket right here is the pocket, but this right here, this cysteine, is the binding site. That's very important for what we're going to get to here in a second. Also notice that there's nitrogens here that are triple bonded. and here, and here. But the most effective of them are these right here. Well, probably help if I actually draw something that don't have free hydrogens around for binding in this pocket. Alright, I gotta go fast so I don't take 5 minutes on this slide again. Here is Embrutin again. Here is ARQ-531. Now, some similarities. This right here and this right here are the exact same. It's because both of these are made to go into the binding pocket that I showed you a second ago. Now the major differences that start to jump out at you is instead of this nice little nitrogen here, you have an oxygen double bonded. And instead of this right here, this nice little carbon-carbon double bond, you have a OH group on the end of that. You see the main difference between these two is that ARQ-531, one does not bind to the cysteine that this one binds to. So it doesn't bind to that at all because it's a non-competitive inhibitor. It doesn't bind to the active site. Another thing is it's a non-covalent inhibitor, whereas all the other ones I've showed you up to this point are covalent inhibitors, which really makes it stand out in this field as something different. Now, all the old inhibitors I showed you were all irreversible inhibitors, and the idea was to just stop the cancer, but the thing is, they are not good enough to kill the cancer, but they are an effective treatment. However, recently, because Embrutinib, I keep wanting to say Embrutin, came out around 2013 as far as clinical trials are concerned. But around 2018, which is about when ARQ, if you look down the bottom left, was spiking up, people started going into remission really bad. And it became more and more frequent because, like I said, cancer mutates. It was mutating that cysteine, causing Embrutinib to not bind to the thing that it's made to bind to and become basically useless. Whereas ARQ not only doesn't bind to the cysteine, so it's still an effective treatment for people who are in resistance to Embrutinib and people who haven't had it either. It's also not as dangerous of a drug to take. Alright, we are really stressed for time, so I'm going to try and speed this out a little bit. But right here I have a picture of BTK, this nice big enzyme right here. And this yellow right here, this is your cysteine. Notice this OH group right here is not actually bound to it, but is still closely connected to the other parts of your pocket. Just in general, this is how ARQ-531 will bind in the pocket and help inhibit it. This is how it works. Alright, this is kind of a crazy one. This is ARQ testing on mice. Mice were engrafted with tumors. They literally injected CLL into mice's tails. And this is the survival rate. So up here you have 100%. And you notice ARQ at 75 milligrams per kilogram of the mouse made it this many days before everyone died. Alright, I've rearranged my PowerPoint a little bit. I am going to go a little bit over on time, but I made this basically the last slide and I added some other graphs of data to the end of it. If you want to look at that, it's fine. If not, that's fine too. It's all notated in the data that I posted along with it. It's in the PowerPoint. But the last thing I wanted to talk about in this last minute is clinical trials. Last year, towards the end of last year, very recently, ARQ-531 went into clinical trials, into testing on actual patients. And it's still new. There's still a lot of uncertainty about it. And the problem with it is, again, cancer mutates. This probably won't be a solution forever. Hopefully we'll come up with a better one. But for now, it's a major development and it can really help save some lives. And it's just good in general that we've coming out with this. It's also helped people to identify new targets for treatments like this. And people are starting to target BTK and things that are not CLL. And just the design of this drug in general is helping come up with other new drug designs, which will hopefully just further help to improve how well we take care of patients. All right, that's everything.